Hello everyone. Today we are going to discuss about the topic is Cayley-Hamilton theorem and its applications. Let us see the definition of Cayley-Hamilton theorem. What is the Cayley-Hamilton theorem? It discovers one of the linear algebra's most elegant, powerful result where matrices satisfy their own characteristic equation. The statement of the Cayley-Hamilton theorem is every square matrix which satisfies its own characteristic equation, which means that suppose the polynomial p of lambda is the characteristic equation of the matrix A, then p of A equal to 0, satisfies the condition p of A equal to 0. So A satisfies its own characteristic polynomial. In mathematical form, the matrix with characteristic polynomial p of A equal to determinant of A minus lambda I, we have p of A equal to determinant of A minus AI equal lambda I equal to 0, which is as the matrix equation. So it's A satisfies its own characteristic equation. The foundation, the characteristic polynomial p of A equal to determinant of A minus lambda I, which is the polynomial, we get p of A equal to determinant of A minus lambda I. A minus AI satisfying this equation. So from this Cayley theorem, the properties of this theorem, degree equals matrix dimension, coefficient related to matrix trace and determinants. Roots are the eigenvalues of A. The following steps involving its applications. First one, finding the characteristic polynomial. Then replace lambda with matrix A. Then verify the result B of A equal to 0, which is 0 matrix. For example, let us considering 2 by 2 matrix A equal to 3, 1, 2, 4. In step 1, finding P of A, P of lambda, that is the characteristic equation, determinant of A minus lambda I. So expand this, we get expand this, we get the P of A equal to lambda squared minus 7 lambda plus 10. How to find the characteristic equation? S1 in shortcut, lambda cube minus s1 lambda squared plus s2 lambda minus s3 equal to 0, which means the given matrix is 3 by 3 matrix. When the given matrix is 2 by 2, the formula is lambda square minus s1 lambda plus s2 equal to 0, which is the characteristic equation of the 2 by 2 matrix. Verification and computing the from given 2 by 2 matrix, we substitute A into characteristic polynomial, that is P of A, which means A squared minus A 7A plus 10 into I. So from A we have to find A squared and also calculate 7 into A, 7A, then substitute A squared value and 7A into this polynomial, so which tends to become 0 matrix, which is equal to 0. So it is verified. This theorem holds our matrix A satisfies its characteristic polynomial equation P of A equal to 0, which confirming the Cayley-Hamilton theorem. So hence the proof. Practical applications are computing matrix power. So higher power we have to calculate the higher power of the matrix in terms of lower powers by using this theorem. So or simplify the complex calculation in engineering systems. So finding matrix inverse, easy to find the higher power inverse powers without row operation or cofactor matrices. Then solving differential system, essential in solving system of linear differential equation, particularly in control theory and mechanical vibrations. From the above example, we can compute the matrix inverse by using Cayley-Hamilton theorem. For the above example, the rearranging the equation becomes a square minus 7a plus 10i equal to 0. Rearranging this equation, so we get a into a minus lambda 7i equal to minus 10i. By solving a inverse we have to multiply by a inverse, so therefore a inverse equal to minus 1 by 10 minus 1 by 10 a minus lambda I. From this a, let us take it to be right side, so a inverse equal to minus 1 by 10 into a minus lambda I. So easily we have to find the a inverse.